So I'm going to talk about scoping rules, a framework for understanding and specifying name binding. So what is name binding? Given some reference to some name, we want to find the corresponding declaration. And it's one of the basic problems in the programming languages, but basic doesn't mean simple. So if you look at some real languages like C++ or other imperative languages, name binding is actually quite difficult to understand and to discuss. So we asked some questions. How can we improve specification of name binding and make it independent of the complicated parts of other parts of specification? And how can we teach it? How can we discuss it? Is there a concise description of name binding rules? So our contributions are, we introduce a bunch of name binding combinators. So we wanted to make it easy to express the name binding rules using combinators. So at any given point when we need to look up a name, we can take a bunch of combinators, we can write an expression, and we can talk about it. So with the combinators, we did some elegant formulas. It's easier to experiment and analyze. We can change things slightly, see how it works, and maybe gain a greater understanding of the problem. But at the same time, we also wanted to include a way to put into the lower level parts of the language, how exactly are the references matched, and what happens under the hood when you do overloading, say, or some other features. But we didn't want to write a compiler. It's not a compiler framework. So we just wanted to abstract those parts and be able to use them in our description. So we will show, I will show application to a couple of scenarios in C++, and C++ has some really complicated binding rules. We all know that C++ is really complicated in general, and so it's too bad, but we will look at some, we will look at some weak hiding extension to C++ concepts and ambiguity experimentation. Those are in the paper. I will not discuss them in detail here, but you can look them up later. So this is an example of, very simple example of how name binding looks in C++. We have a use of a name calling the function foo, and then we have a bunch of namespaces with a global namespace. And in the first scenario, question in this very simple scenario, the question is which of the foos will actually be found for that reference. Here's another example. This is based on an extension to C++, a concepts extension where one can declare concepts with a bunch of interface available to templates, and then one can constrain template parameters and use this interface. And here the question is, what happens when we want to call a function that has the same name from an external scope, not from a concept? Is this function hidden, or are we able to call it? This is just an example here. So what's the state of the art to talk about name binding at this time? So in C++, some of you may have seen the standard. It's the standard is. It's a kind of semi-formal English description. English language description is several hundred pages long. For the C++ name binding specification, those are some of the important chapters. So if you want to understand how you will look up a function name, you have to go through lists of special cases, and you have to understand what happens when you are in this situation, what happens when you are in that situation. So we found that it's really hard to understand, and actually, interestingly, many compilers that are considered mature still get some small things wrong here and there. So our name, the goal of our name binding framework is we come to a place here, we see this foo, and we have some scopes generated by the compiler. We don't actually generate these scopes, we assume that they are there, they are given by the compiler. And we want to, given a reference and some scope, we want to either get a declaration or an error. And our bind is composed of lookup and resolve, which I will talk about later. So the first step is using our combinators is to describe the situation that we are looking at. This is just to give you a taste. I will talk about the details of the combinators a little later. But you want to be able to write such an expression to describe how these scopes relate and what is the final scope that you will use with the binding framework. And the second part is to actually execute this scope, to execute this bind. And this is where the abstract specification of the language properties comes in. So on the one hand, we can experiment with those abstract descriptions of the binding situation. And on the other hand, we can experiment with some programming language features. So I will actually first talk about our abstraction of the language very briefly to give you an idea what are we abstracting from. So our binding, like I said, is composed of lookup and resolve. So given a reference and a scope, we first look up the reference, and then whatever we have, what we have been able to look up, we pass to resolve. And resolve is not lookup, it's for example, it abstracts from overloading, ad hoc overloading in C++ and other features like that. So lookup is purely syntactic, and resolve does some semantic decisions. Okay. So we need to find some minimal abstraction. So as for now, all of these functions, the context here is just parentheses. So for lookup, we have, or rather for our purposes, what we needed to get is this match. We needed to be able to just match a reference to a declaration. This was the underlying language property. So for example, in C++, it's quite simple because in most situations you just have to match the names. You don't actually look at the types. You don't have to. You may have to look at kinds, but you don't have to look at types. And for resolve, and once we finish lookup, so the lookup is generic in terms of match, we get an overload set. And for resolve, we pass the overload set in, and then we use this select best variable, which basically performs overload resolution and so on. So given an overload set, we get possibly a declaration. And before we so here we get a bunch of perhaps viable things. The final thing that we do is assess, and we have factored out ambiguity. So we may change the designs in the language for certain cases when ambiguity occurs, what to do. So this is just one possibility, and it really depends on what would you select. It depends on what you want to experiment with. So we wanted to experiment with ambiguity, for example, and we have made it into a specific low-level language feature. So here's the resulting language abstraction. We have ambiguity, and then we have match, and we have select best variable. So those are the three things that we need to know about the language. And now we'll talk about how do we actually create these scopes from smaller scopes. So we have 4 combinators, and we have hiding, which is basically shadowing or whatever other name you want to use for it, where names hide other names, merging for merging different scopes together. Opening is a little bit of a strange one. We had to design it for describing argument-dependent lookup. So argument-dependent lookup in C++ is one of the most confusing parts of name binding, where the names of lookup depend on the arguments that you use them with. And then we have weak hiding, which we have used to describe some features that we were playing with for C++ concepts. So weak hiding is not a purely syntactic operator, while hiding is a syntactic operator, purely syntactic. So here are the combinators. Basically, a combinator takes two scopes and returns another scope. So for merging, we take the results of lookup into scopes and union them. For hiding, we check if the lookup succeeded in the first scope. So we return the results from the first scope. Otherwise, we return the results from the second scope. For opening, we actually check if the lookup succeeded in the first scope, then we will look into second scope. Otherwise, we will not do anything. And for weak hiding, we include, in this condition, we include the results of results. So it's not purely syntactic hiding. We actually check if there was something that we can use. And if there wasn't, then we will go to another scope. So those two are pretty similar. As you can see, there are the special cases of a conditional combinator. Then this weak hiding, as I said, is used for concepts, for experimentation with concepts, and this opening is for ADL. So now I gave you some overview of what we have, and I will show you a couple of examples. So ADL, argument-dependent lookup. Basically, we have two namespaces here. We have a bunch of declarations of who. We have a struct x in namespace 1, and then we have a definition of who for that x. When we call foo of x here, where x is of this type from that namespace, we perform argument-dependent lookup, and here as well. So we have two functions, we have three calls, we have to talk about. So this is this discussion reflects how we actually started with that, how we had to discuss this, and we had to use some notation to put on the whiteboard and talk about it, what's going on here. So we started looking at these combinators. So for the first call, we basically say that we use the namespace of the function itself, then we use namespace 2 because of that using declaration. We have to look for food in here, and we merge those together. And then we do this strange thing, because in general, we have to do kind of scope working. We have to check at the current scope, and then if we didn't find anything, we have to go to the next scope, and so on and so on. So we open the scope of namespace 1, which is the argument namespace, only if we found something in here. So it's a strange thing, because in C++, when you have those using declarations, when you work the scope, if you find something in the using declaration, you have to make sure that you put in argument-dependent lookup right there. You cannot wait for later, because later on you can get some errors and other problems. So you have to put it in right away. And then we have we find another loop in the global namespace and the argument namespace. In the second situation, it's much easier. There's no using declarations. We just have to look for food in here, and we hide all the declarations from other namespaces, from the global namespace and from the argument namespace. So this code will not succeed because of this declaration here. But then if we open another scope, the situation changes. So this scope gives us a fresh situation where we start looking into here, and only if we don't find anything here, we'll go back. So for the third scope, for the third situation here, we look at the current scope, we then look at the scope brought in by the using declaration, and then we actually have to look at the argument scope. And then we look at the surrounding scope around this log scope, and finally we look at the global scope and the argument scope. So we notice some similarities here. We try to come up. So now we got those three particular situations, and we are trying to come up for a general description for any situation that includes argument-dependent lookup. So we replace all of these here with this F, which basically takes the current scope, using declarations from the current scope, and if there is any using declaration, we will look in the argument-dependent lookup in the argument-dependent scope, but it will be hidden by the current scope. So if we find that here, if we find something in the current scope, we cannot look into the argument-dependent scope. Then we have those are particular situations here. So for those two places, the using declarations are this, and here we have nothing. Okay. So this is our generalized expression for lookup using ADL and C++. And as you can see, it's quite complicated, and it really is like that. If you check, if you look at our examples, it really is that complicated. So it's very hard to understand, and most of the time you won't hit these very complicated situations. But when you do, you may be really wondering why you're getting an error. So first, we look in the surrounding declaration of the call using that FADL, which is very similar to what we've seen before. We look at the current scope, we use using declarations. If there were any using declarations, we open up ADL, but we hide whatever is in the current scope. And this is a special one. We hide any names that are not function names. So for example, if you have a variable name, it will just hide all the names, all the same names from the argument. Then we do the same thing for all the surrounding block scopes, and they conspicuously hide each other. So block scopes are a little different. And then we do this for the surrounding namespace scopes. So for namespace scopes are slightly different than block scopes in C++, and the only difference really is that a declaration in namespace scope does not hide the argument-dependent declarations. So in block scope, if you have a declaration, it will hide argument-dependent declarations, and in namespace, if you don't have, even if you have a declaration in the namespace, it won't hide argument-dependent declarations. So I hope this is slightly clear. And again, just to reiterate, our goal is not to compute, for example, ADL. That, as for now, has to be done by the compiler. So the compiler has some rules on which declarations are relevant to an argument. Okay. So here is the C++ operators example. Looks very, very simple, but we run it through 4 or 5 compilers, and out of the 4 that we described in our paper, only one of them got it corrected. So GCC and Clang both accepted this reference, but didn't accept this one. Sorry, they accepted this reference, but didn't accept this one. But then Intel compiler, at least it was consistent because it accepted both of them. So that's good. And then Camo compiler, which was the only one that did it correctly, and Camo is not even available. It's just available through some online interface where you can type in your program and compile. So it's a very old compiler, but it properly rejected both of these calls. And actually, we had some hard time ourselves finding which of those compilers was correct, because when we opened the standard, it was a long list of special cases for the built-in operators. So we figured out that this is the basic scope expression for operators. So you can see that if we have an operator found in any of these scopes, including this one, so we have an operator here, it will actually hide all the operators from the global interface. For some reason, GCC and Clang do not do this for that for expression, but when we call it explicitly as using the function syntax, they actually see that this should be shallow. So then, after reading the things more carefully, we came up with a kind of more general description of what happens for operators. So with the current scope, the using expressions, the built-in operators, and the members of the first argument with operator call. And then you look in the surrounding block scopes and surrounding namespaces. And if you add ADL, it starts looking a little bit more like before, but just we have to take care of these built-in operators and members. Okay, so in our paper we have some more applications. We talked about weak hiding for concepts, and we had some experimentation with ambiguity. Well, so conclusions. Our goal was to make things simple, and we thought that combinators are a great way to do this. You kind of can write something that resembles algebraic expressions. So it's clear and concise, and it's really great to discuss things on the whiteboard and actually understand what is going on in a language. Then we have the language abstraction to distill the most important properties of a language. We came up with 3 of these, but this is not set in stone, whatever you need for your purposes. And then the important thing to stress is this is not a compiler system, so it doesn't actually, don't have any grammar abstraction. We are not there to extract those namespaces. Once you have the namespaces, we can use our combinators to describe how they are combined. But in the future, we would actually like to add another aspect to this, where we can integrate this with the compiler, including building up the namespaces and then actually calling those expressions in the compiler. Thank you.
Thank you. It's very nice work. And while reading it, well, indeed, it's very nice to have a unified representation given the diversity of programming languages and conventions for name resolution and reference binding. But while reading your paper, I kept wondering whether you had another application in mind, and you didn't mention. In fact, the problem of finding a uniform representation of name binding algorithms is being solved consistently in the community which is developing the IDEs, the integrated development environments. And I'll explain why. Because the IDE, it usually provides a framework to implement different programming languages on one platform. Like there is this whole family of IDEs derived from IntelliJ, and there is one for Ruby, for Python, and they all use the same platform. Because there is a uniform representation of name resolution machinery. And once you get this machinery, what you get for free is rename refactoring and semantic search and refactoring, which have to do with moving and extracting new concepts so they can see whether the new name clashes or not. So I think these are the real clients of the framework that you are developing. So having this uniform interface, which specification developer can describe the language in, and the IDE will just implement and have all these goodies for free. So I wonder, have you looked at any of the implementations of IDE naming machineries? Because your rules for processing this resolve and merge, and I don't remember the notation, well, this operational semantics you give into your combinators, it's really reminiscent to what people do in the IDE's implementation. So the question, have you been aware of any of this?
We have not looked at this specifically. We're more in mind. We had compilers in mind. We were thinking, seeing how the compilers are inconsistent. You probably could do this for an IDE, but you would have to implement the salient part of the language, as we call them, the most important, those primitives. So perhaps you would kind of re-implement the compiler partially at least, but about IDEs, an interesting thing is I mentioned those compilers giving an error on the operator expressions, and actually we also tried it with the Microsoft compiler, and the Microsoft compiler didn't do the right thing. It accepted one of the calls but not the other. But the IDE properly flag both as the error, because apparently the IDE is using a different compiler front end than the compiler itself. So that's
probably more generic. Yeah. Okay. So another more. Okay. Okay. So let's then proceed to the questions from the audience. If there are any. Yeah.
Yeah. So I haven't dug into those IDEs myself, but I do know that one way of doing attribute grammar, but they're really tightly tied to the grammar of the language. And what this is a system that gives me what attribute grammar might otherwise give me, but the syntax is out of the equation. It's more general.
Yes.
Yeah.
But this is what is.
I don't know if it's more general, but it has a different purpose, I would say. And writing a grammar for C++ has been attempted many times, and I'm not aware of a successful attempt at this point. So most of the compilers are really, they mix the grammar with the semantic analysis, because C++ has a lot of semantic interpretations in the grammar. So it's very hard to take any principled approach and apply it to C++.
I was just wondering, in the process of putting together your generic representation, and in the process of translating the spec ease into a formal application, were there any sort of things that leapt out of you as being wild, blatant inconsistencies in the informal, semi-formally expressed rules, and things which, if you had a formal representation, you would immediately see that doesn't work. That's not the right thing to do.
Actually, to the credit of the C++ designers, we haven't really found any glaring inconsistencies. The things in the standard are quite well thought through, and I am just very surprised sometimes how they actually managed to write down those 700 pages in the original standard and not make any errors. And the complication of the rules actually comes from all the thought put into it, because ADL looks like a very complicated feature, but actually in the real world it's a very convenient feature, and it's rather necessary because it extends public interfaces of types to the things that you would expect to be included. So if you have a class, for example, it's not just the members of the class, it's also the free functions from the surrounding scopes and so on and so on. So we haven't really found any inconsistencies. The only problem with the standard is that it's very spread out to different parts, and I'm sure that the people that wrote it, they knew what they were doing, but I don't even know if they remember anymore. But it's very hard to really read this and understand it. And if you want to discuss it, it's you always find yourself going back. Oh, did you look at the paragraph 14.1.3.7? And something here that we have missed, and we thought that it would be nice to have something that we can.
Yeah, I get related. Do you know of any other examples where standard ease has been turned into something more formal? Or is it, yeah,
just a very few isolated examples. So my thesis, I have turned a part of the standard ease into something more formal to be able to specify concepts. Jeremy Sieg has a long time written a paper about templates, where he has turned the parts related to templates into specification in Isabella Latin, and then he proved some properties about this. So there are isolated, places, but nobody has attempted the whole thing. I don't think so. There were also some papers about memory models where part of the C++ memory model was taken as a separate thing.
Yeah, so related to the previous question, did you find any, given your new notation, did you find any opportunities for maybe simplifying the rules that you saw, making them easier?
No, unfortunately not. Like I said, the rules are complicated, but they are there for a reason, and they are really the way well thought out. There are few well-known cases in C++ that are maybe hard to understand, like the flexing parse or whatever it's called, I forgot, where you think you wrote something, but it turns out to be a function declaration and not a constructor for. There are a few things like that, but they're very, I would say that they are a few fewer and far in between, so there's no major things that you can re-simplify. You can use another language, but if you want C++, then not so much.
All right. Let's send the speaker.